Now we're going to be looking at the physical properties of carboxylic acids. In the past, we've always referred to oxygen as being rather close to fluorine on the periodic table, meaning that oxygen is very electronegative. As a result, the electrons are being pulled in by the oxygen. The electrons are drifting from the carbon to the oxygen. And we saw that several other times too. For instance, in a ketone, these electrons are drifting towards oxygen. And then in an aldehyde, once again, these electrons are being drifted towards oxygen. The difference with carboxylic acids, though, is that it's happening in two different locations. It's because carboxylic acids have two oxygens, it's giving it two locations in which the electrons are more dense, where they're occupied more. Because of that, it'll have strong interactions when it comes to water. Water as a molecule is H2O. And how that looks is oxygens in the middle surrounded by hydrogens. Oxygen, once again being very electronegative, is pulling those electrons towards oxygen, which is giving oxygen a partially negative charge, but it's also giving hydrogen a partially positive charge for the same reason, because it's having less electrons. So that means when we mix it with water, this partially positive is interacting with that partially negative, and there's an attraction there. That attraction is called hydrogen bonding. Remember, hydrogen bonding isn't a true bond, it's an attraction. So it's happening down here with the OH group, but it's also happening up here with the carbonyl group. It's still going to have the exact same attraction for the exact same reason. So we saw that attraction with ketones and aldehydes before. And now we're going to see it with carboxylic acids, but we're going to see it twice as much because there's two different locations of the oxygen. So if we take another look, this is the hydrogen and this is the oxygen of the water. And so if this is the oxygen of the carboxylic acid, there's an attraction here called the hydrogen bond. This is making it very soluble in water, especially if it's less than 4 carbons. Even after that, after you pass that 4 mark, it's still soluble, just not as much. Now let's look at the reason why it's considered an acid. An acid in general is a compound that donates a hydrogen, or that loses a hydrogen in the process of a reaction. Well, if we look here at the carboxylic acid, and we take a special close to this look to that OH group, and we go back to the electronegativity that we were talking about just before. The electrons are drifting towards the oxygen and away from the hydrogen and the carbon. As a result, this hydrogen here becomes very vulnerable, and it makes it want to pop off to get donated to a reaction. And that's actually essentially what happens. The hydrogen at the end here ends up being removed, and which is why you do not see it on the right-hand side, and it gets absorbed by the water, which is why it's H3O. Notice the negative sign. That's because the electrons from the hydrogen were donated to the oxygen once the hydrogen finally leaves. So that's leaving oxygen with an extra electron. Whereas H3O absorbed that hydrogen, which means that the hydrogen lost the electron, so it's a positive charge, which means now the water has a positive charge when it's H3O. Alright, write a balanced equation for the ionization of butanoic acid. This looks like a very hard question, but if we break it down, it's not so bad. Ionization just means that we're producing ions, which means at the very end, you're going to have a positive and a negative. So let's first take a look at what exactly we're talking about. Butanoic acid. We know that but is 4, so that means we're going to have 4 carbons. Oic acid means it's a carboxylic acid. Which means we will have a double bond on the oxygen and an OH group. Like I said, these questions aren't that bad. You just have to take them step by step and break it down. It's in water, so that means we're adding water to it. As we just said, this hydrogen at the end is the one that's vulnerable, and that's going to be the one that leaves. So this donates its electrons to the oxygen, and then it moves towards the water. So when we rewrite it, now it has a negative sign, and that's where the ionization comes in, because you just produced an ion. You got rid of the hydrogen, and now you have something with the charge, and that's an ion. And in the process, the water then absorbed that hydrogen. Once again, you have a positive charge now rather than neutral. Once again, they're producing an ion, which is part of the ionization. Identify the carboxylate ion. Well, the carboxylate is what's produced after you take the hydrogen off. So that's your carboxylate ion. So we start off with the carboxylic acid. The hydrogen is removed, which is why you have a negative sign. That's your carboxylate ion. The hydrogen goes over to water, producing the H3O plus with a positive sign. Now let's take a look at carboxylic acids, salts. So it's essentially the same thing, where we have a hydrogen here that's very vulnerable. So the oxygen comes over and takes it away, and the hydrogen then donates its electron to what it was originally attached to. Well, because of this negative sign here, it gets attracted to the positive sign of the sodium hydroxide. And so those two come together. And remember, the term salt is a generic term for any ionic compound, which means it's a compound that's going to have a positive and negative in it, which is why you have a positive from the sodium and a negative from the carboxylic acid. It's considered a salt because it's an ionic compound. These are used for preservatives and flavor enhancers such as MSG. So just to give you some idea of where they're used, sodium propionate is used to use in cheese and bread to prevent mold. Benzoate inhibits the growth of mold in fruit juices and margarine and things along those lines. And then MSG is a flavor enhancer for fish and meats and vegetables and so on and so forth. And there is our compounds. For instance, sodium propanoate. So prop means that there's 3 carbons. The O8, the 8 at the end, is referring to the fact that it was run to carboxylic acid, and now it's a salt. And then the sodium is what it's bonded to make it a salt. So carboxylic acid salts, ionic compounds with strong forces. That's because it's a positive and negative interaction. They're usually solids at room temperature, just like all salts. Think of sodium chloride. It's a solid. Just like other salts, it has a high melting point. And once again, it's usually soluble in water, so it's going to dissolve. So let's look at propanoic acid mixed with these two things. Once again, this question seems really difficult, but if you break it down, it shouldn't be too bad. We're starting off with propanoic. That means that prop is 3 carbons. Oic acid means it's a carboxylic acid. Which then means you have a double bonded oxygen and an OH group. We're mixing it with water. Now this should start to look familiar to what you've done a little bit earlier with removing this hydrogen and putting it over to the water. So let's do that. Double bonded oxygen, and the oxygen, it would have an OH, but because we lost that H, it's just going to have a negative sign. And water absorbed that, so it's H3O rather than H2O now. So let's do the other one with KOH. Exact same starting compound with KOH. So this hydrogen becomes removed. So just like we have in the question above, we have a negative sign. But this time, since it's OH here rather than water, when we combine it to have one hydrogen, we now have 2 hydrogens. So it actually produced water in the process. That means this K is floating around in solution. So it's going to attach itself to that oxygen. And there you go. Here's your negative and positive interactions. And that is the end of the properties for carboxylic acids.